Hi everybody, in this video we're going to continue with Chapter 5, Proofs, specifically 5.4, Mathematical Induction. So let's go straight to example 5.24. And it says, prove that the sum of the first n natural numbers is given by this formula. So this is what is called the statement. So this is our statement, and notice that it's in terms of n. Now when you do mathematical induction, the first step is to test for a value n. In this case, we're going to test for 2. So S of 2, according to the statement, is going to be 1 plus 2. And then it should equal 2 times 2 plus 1 divided by 2. And then obviously we get 3 on both sides of this equality. Therefore, it's true for this example. The second step is assume that it's true for k. So that would simply be substituting n with k. Then the third step, which is the inductive step, is to prove for k plus 1. So how do we prove? Well, normally we use the previous statement to get to this expression. So this is what we're going to do here. We're going to add k plus 1 to both sides of the first statement. So this part, with this part here, I should arrive to this answer. We'll continue that over here. Notice that it's equivalent to that. And the final step. Since we have arrived to the same answer, we have proven by mathematical induction that the statement is true. Now we're going to do example 5.26, and it says, prove that 3 to the n is less than n factorial for all integers n greater than 6. So this would be our statement. We need to always have that clear. And then the first thing we do is test normally the first value for which the expression is true. In this case, 7. So we would do 7. And that's just that 3 to the 7 should be less than 7 factorial. And we see that this is true because 3 to the 7 is 2,187, and 7 factorial is 5,040. So it's true for this statement. Then the second step, as usual, is assume it's true for k. So we would just write the statement. And then the third step is to prove for k plus 1. So again, we need to get from here to here. So let's write this over here to the left. Since I need to get this expression k plus 1, I'm going to multiply both sides of this inequality by 3. And notice that I get the expression 3 to the k plus 1 is less than 3 times k factorial. Now we don't have this yet, but notice that 3 is less than k plus 1 since k has to be greater than 6, as was established here. That means that there's no problem with substituting 3 for k plus 1. So we could rewrite this as 3, and then here we write k plus 1 times k factorial. And then notice that this here is equivalent to k plus 1 factorial. So we have the proof. So through mathematical induction, we have proven the statement to be true. So next we have example 5.27, And it says, show that in an arithmetic sequence where a sub n is equal to a sub n minus 1 plus d, the nth term can be given by this formula. So this would be our statement right here. And then we start with the basis step, or step 1. The basis step here will be testing for n equals 1. So that means that the first term is equal to the first term plus 1 minus 1 times d. And then this implies obviously that a sub 1 is equal to a sub 1. So this is true. Then for the inductive step, that's also steps 2 and 3, right? So the inductive step first, assume that it's true for k. So we just write everything in terms of k. And then we need to prove for k plus 1. Notice that this is the same as saying first term plus k times the common difference. So this is what we have to prove. Now, we're going to proceed a little bit differently. We're going to use this fact over here. Notice that we can write a sub k plus 1 as a sub k plus the common difference, right? This is just this over here. This just means that I can get the next term with the previous term plus the common difference. But I previously said that a sub k is equal to this. So let's substitute that in here. And notice that we're going to get that a sub k plus 1 is equal to this expression. But then if I distribute this, what am I going to get? Notice that I'm going to get that this is equal to this. And this cancels out with this. So notice that I arrive to the proof that I was looking for. So that means that this statement is true, and we have proven so through induction. So next we have example 5.29, and it says, show that 3 divides n cubed plus 2 times n for all non-negative integers n. Okay. So this here would be our statement, right? 3 divides n cubed plus 2n for all non-negative integers n. And let's call this statement P of n. Then we have to start by proving one case, like P of 1. Notice that this is going to be 1 cubed plus 2 times 1, which equals 3. And this is obviously divisible by 3. We're going to next assume that P of k is true. That is, that k cubed plus 2 times k is a multiple of 3. And what we have to prove is P of k plus 1, and that's going to be k plus 1 cubed plus 2 times k plus 1 is divisible by 3. Now what happens if we expand this a little bit? Notice that this is equal to, and then once we have this expression, we need to use the previous fact. Notice that this we said is a multiple of 3, so we can group that, and we have k cubed plus 2k grouped together, and then put everything else together. Notice that we get 3k squared plus 3k plus 3, which can be written as, so notice that we said previously that this is a multiple of 3, and this is also a multiple of 3, obviously, because it's being multiplied by 3. That means that we have proven that the statement is true through the method of induction. Okay, so here we go now with example 5.30, and it says, using mathematical induction, show that for all non-negative integers n, this equality is true. So this would be our statement, right? Now notice that this is the sum of combinations. So the first step is to test it for a value such as 1. And notice that this would give us 1 in combination with 0 plus 1 in combination with 1 should equal 2 to the power of 1. And this is true because this is 1 plus 1 equals 2, and we all know that that is true. Then we're going to assume that it's true for k. So assume that this is true. And we write it as well, right? This would be, and then we have to prove this to be true, right? Prove for k plus 1. So this proof we're going to do using a principle that we learned in chapter 3. I don't know if you guys remember that. We had to show that this n in combination r minus 1 plus n in combination with r is equal to n plus 1 in combination with r. This is something that we proved in chapter 3. If you don't recall it, I would recommend you go back and review it. So in order to make this proof, what we're going to do is add. So notice that we can do this. And then we're going to add this to itself. But we're going to shift the bottom part left. And this would also equal 2 to the k. So like I said, we're going to add this. So notice that we're going to get the following. Now this comes from this principle that we mentioned before, right? And then notice that this is the same as saying 2 to the k plus 1. And here we have the sequence that we were looking for. Now you might say, well, no, because this last term and this other term are not in this k plus 1 form. But notice that these are all equivalent. They're all equal to 1. So using mathematical induction, we proved this statement to be true.